High-powered electronics oftentimes use GaN, some use silicon carbide. Together, they have a better solution. So you tell us about what we'll be seeing.
Right, so we have various demos to show you. We're focused on three core areas, which is mobile, data centers, and electric vehicles. And we have for solutions, Navitas, we're a pure play GaN and SiC company. So we have for solutions which involve GaN, SiC, and both together to have a full optimized solution with the highest efficiency, performance, reliability for our customers out there.
Okay, so let's talk about the GaN solution first.
Yes. So on the mobile side of it, we are number one in GaN fast chargers with over 250 million pieces sold. We're in extensively a lot of the chargers out there. Any GaN charger you would buy is typically with Navitas inside of it. And we've got some demos to show you which shows the next generation of switching improvements, miniaturization, efficiency improvements, which show how small we can get now to charge laptops in the same size as what we used to charge iPhones a few years ago. So that's from the GaN side of it. GaN is also getting into the more consumer side, so TVs, 8K TVs require about 5 times more power than a 4K TV. So it requires more power delivery. GaN is perfect for that. And then also stuff which you wouldn't really kind of consider, like washing machine drives, motor drives, light industrial drives. GaN is becoming increasing its adoption into these types of markets, which is very, very interesting for us.
Okay.
So that's from the GaN side.
Okay, how about silicon carbide?
So silicon carbide is a more rugged device. It's kind of designed for hard switching. We have some solutions which are the higher voltage. So for example, for electric vehicles, which need an 800 volt bus, they need a 1200 volt device to block that voltage. So silicon carbide is the choice. And we have this example of a 22 kilowatt onboard charger, which uses silicon carbide. It's got very high power density, kilowatts per liter. And we can show you the comparison between a silicon solution versus the silicon carbide solution.
Okay. Now, combining GaN and silicon carbide.
Yes.
Why and what do you have?
Yeah, so we offer both GaN and SiC, and we investigate both of them in our solutions to determine which has the best efficiency and performance. Now, our data center focus falls perfectly into this, right? So a data center, the efficiency is critical. It has to meet titanium specifications, which is 96%. We've just released an 8.5 kilowatt for hyperscaler data centers like next generation. High power density, high efficiency requirements. We've achieved 98% efficiency. And by doing this, we used silicon carbide for the front end PFC, and then we used GaN for the LLC side. And by combining these two technologies, you really see the benefits of the efficiency, the speed, the miniaturization, and the performance. Something very interesting I want to point you to is this. Now, as you can see, this is a 5-watt iPhone charger, been around for a long time, right? Now, that uses silicon, right? The GaN solution, and the same size, somewhat, is a 30-watt, or here it is a 30-watt solution. And that uses our GaN, it's the same size, but it's 6 times more powerful, charges faster. Now, going forward here, this charges kind of tablets. Now going forward, this here is a 90-watt peak power charger. So this is now looking at laptops. So from here, going from the iPhone, now we're looking at pretty much the same size, which will be doing your laptops. And this will be out in production next year, basically. We have an 8K TV power supply. Now, 8 kV needs about 4 times to 5 times more power than a 4K TV power supply, just to do all that, the resolution, the data transmission. And you can see here, this is a silicon solution. There's a lot of heat sinks. It's thin, but there's improvement. Now this is the GaN solution. We're able to switch faster, more efficient. So the heat sink, the cooling requirements have shrunk. which has a good effect when these go on the back of an LCD or LED. You don't get the heat spots, and it doesn't affect the color and the pixel characterizations. We use planar transformers to keep it thinner. And here, this is a very thin design. Here, this is an auxiliary power supply for a washing machine. Now, on a washing machine, you have an LCD display. That needs a power supply, and this is typically what you have for it. This is a 60-watt power supply using silicon. See, we've got heat sinks, and we've got a couple of inductors, and it's pretty bulky. Now, using the GaN solution, here we can really minimize the size. We can improve the efficiency, minimize size, and the key thing is here we can reduce system cost. And same with a washing machine motor drive. I talked about motor drives before. This is a typical 700-watt motor drive drum drive. And you can see here you have a typical IPM, intelligent power module, 6 IGBTs and a gate driver inside. And that switches the motor. You have a heatsink, a very bulky, expensive heatsink, what sits on top. Now going to the GaN solution, here, these are the half-bridge GaN's GaN Sense motor drive ICs. No heatsink, 700 watts, smaller, thinner, more efficient, and cheaper. So by eliminating the heatsink and all the peripheral around it, we can really integrate and go for a smarter solution there. And here you can see we've got a silicon versus our solution, and I can explain this all to you. So right now we've got the silicon solution. It's very heavy. It's a 6.6 kilowatt onboard charger. That's what sits in your car for a typical 400 volt battery. Now that is from a power density point of view, 0.8 kilowatts per liter. This is the GaNFastis solution, which has both our GaNFastis SiC and our GaN Safe, high power GaN Safe devices in there. This is 6.6 kilowatts. And from a power density point of view, this is 3.9 kilowatts per liter. So this one's 0.8 and this is almost 4. So it's a huge increase in power density, in weight and efficiency, which means better battery lifetime and mileage range. Now this solution's for 800 volt buses or 800 volt batteries. This is a 22 kilowatt bidirectional onboard charger, and you can see it's almost the same size. Actually, it's smaller than the 22 kilowatt. This has power density of 3.5 kilowatts per liter. And this uses our GaN SiC Gen 3 Fast because it's a 800 volt bus. It needs 1200 volt devices to block it, so it's pure silicon carbide design. Now, moving to one of our customers, BrightLoop, who are very popular in Formula E and heavy-duty industrial equipment. This is a 250 kilowatt. So that's 22 kilowatts. This is 250 kilowatts. This is a high-voltage DC for fuel cell vehicles. And this is designed for like the heavy-duty industrial. But BrightLoop are like cutting edge. They really squeeze the power density into this. Here we have our optimized silicon carbide MOSFET die designed specifically for EV traction. So EV traction requires a different type of optimization where the power cycling is very harsh. When you put your foot on the accelerator in EV, it will take a lot of inrush current and power. So you have to make sure you sinter the devices. You need a different metallization. You need to be able to sinter them, but also the reliability has to be of an excellent quality. So we have optimized our die to achieve these requirements in EV traction. So this is our data center section. Here we've just got a comparison of a silicon power supply versus one of our GaN power supplies. Here you can see this is a 3.2 kilowatt power supply, and you can see that's using silicon. And here you can see the GaN version here, which is significantly smaller, higher efficiency, and performance-wise is improved too. So we use, for data center, we've got a big focus on it. We have a design center which is dedicated for data centers to showcase the improvements SiC and GaN has on legacy silicon solutions. We have a team what work on this, and I can show you a couple of things. This is a typical server rack with the hard drives going here. You have the fans blowing air over the 2 CPUs here. You've got the memory. And in here, this is where you have the power supplies. So you have 2 power supplies. We call them common redundant power supplies. Just if one fails, you've got the backup. This is kind of a standard. And that's the standard size. Right now, these CPUs, they use about 300 to 500 watts. Going forward, you're going to see these change to GPUs, which need more power for the data computation. The Blackwell NVIDIAs are going to 1 kilowatts to 1.2 kilowatts. So, 3 times to 4 times more power requires 3 to 4 times more power here as well. So right now, say you've got a 1600 watt power supply, that is now going to the 4.2 kilowatts, 4.5 in the next generations. So we made a 4.5 kilowatt. This is the world's highest power density AI data center power supply unit designed for these architectures. And we've released that a couple of months back. So that's a conventional one. The next stage is something called the OCP guidelines, where they're looking at next generation data centers for hyperscalers. So this has a different architecture now. They're going to take away this modular section, and in the cabinet, they're going to have these now, and these are the power supplies. These will all go in the rack, several of them depending on the power requirements, and you're going to have this centralized rack of power in the cabinet, and then the servers on top will be just computation. So you're going to have a few GPUs all computing, and then at the bottom or the middle, you're going to have a section just for power.